Hi, welcome back to the course Computer Vision from Scratch. In today's lecture, we will be spending time on 4 topics which will help us minimize overfitting in our neural network. So we will be discussing about regularization, dropout, early stopping, and batch normalization. You may or may not have heard of these topics before, but don't worry, I'll be speaking as if you are a complete beginner. I will also give you a brief recap of what we did in the past 2 lectures, so you have enough context, even if you are watching this lecture without the prior lecture memory. So we'll be covering about what we did and what we are trying to do in this lecture to make our model a bit better. All right. So before we start, as always, I just want to take a moment to just communicate to you that starting something is very easy, but finishing is not. And all of us have started learning computer vision for a specific reason. We want to become really good at this so that we can solve problems that are relevant to people in research or in industry. So since you have already started this series, let us take a small pledge to make sure that we will finish this all the way to the end. If you have a friend who would like to learn along with you, keep each other accountable, or you can even just publicly comment so that you will keep yourself publicly accountable. Whatever works for you, feel free to do that. But let's pledge that we are finishing what we have started. With that, let's do a small recap of what we were doing in the last 2 lectures. In lecture 3, we built a linear model for classifying the 5 flower dataset. So our dataset was something like this. We had different type of flowers: daisy, dandelions, tulips, then 2 more. What were those? Let's open the dataset. Yeah, these were the dataset: daisy, dandelion, tulips, sunflowers, and roses. So we have dataset of images consisting of flowers in these 5 categories. So we are doing a 5-class classification. So first we thought, okay, instead of directly jumping into deep convolutional neural network, we will start with a linear model which has no convolution operation, no activation function. It's simply what it does is, this is the architecture of the model that we followed. Let me just scroll down. So we had the RGB image. We converted it into a flattened layer where RGB pixels are like a one-dimensional vector. Then we had a fully connected connections going from this flattened layer into the output layer. At the end, we had softmax. Although it's technically an activation function, it is used only to convert the final predictions into output probabilities. And we saw that this model was very bad. The classification accuracy was close to 45-50%. So what we did in lecture 4 was we thought, okay, maybe we can make the neural network a bit more complex. So we added one more hidden layer. This hidden layer had 128 nodes in this particular lecture. We were having fully connected connections from this flattened layer into the hidden layer. It was fully connected from hidden layer 2 into the final output layer. It was again fully connected. And here we were using ReLU, rectified linear unit activation function. But here also, to our complete surprise, although this was a much more complex model, we saw that the classification accuracy was not improving that much. We could improve it a little bit, but yeah, our loss came down by an order of magnitude. So the linear model loss was between 10 to 20. Our loss came down with this additional layer and activation. Our loss came down to between 1 and 2. So of course that happened. However, that did not result in increased classification accuracy. But what was happening, as we discussed in the last lecture, last lecture, was that the predictions were becoming more confident, meaning in the softmax, instead of, let's say, having 0.1, 0.6, 0.1, 0.1, 0.1, here the prediction says that the highest probability is for class number 2. We were getting something like 0.25, 0.9, 0.25, I mean 0.025, 0.025, 0.025, etc. So it was making the same prediction, but more confidently. Because of that, loss was decreasing, but the total number of accurate predictions for all the images in the test dataset, that was not increasing. So accuracy more or less remained the same. Then in the immediate lecture before the current lecture, what we did was we decided to do hyperparameter training. And in this hyperparameter training, we decided to change the number of epochs. We decided to change the learning rate. We changed the batch size. We changed the image size, etc. And to do this hyperparameter tuning properly, like like a professional rather than like manually copying, pasting the code in multiple Google Colab accounts and running them parallelly, we decided to use weights and biases platform. And what we did was we wrote the code, which was a very minimal modification to our earlier code, such that we can automatically log the experimental results into weights and biases. So that is what we discussed in the last lecture. We also went through the results that were plotted in weights and biases platform for various hyperparameters. But we saw that even when we changed the learning rate, even when we changed the number of epochs or the batch size or the image size itself, we were not getting significant improvement. And we in fact also realized that perhaps a lot of overfitting is happening. And this graph is a classic example of overfitting, because here you can see that training accuracy is continuing to increase while the validation accuracy has kind of plateaued and then it started to decrease, which means the model is now trying to memorize the features in the training data set, which is almost probably noise. And that is why in the validation data set, the model performance is deteriorating. And this is a classic sign of overfitting. So in today's lecture, what we will be doing is to figure out various ways in which we can minimize the overfitting. And by that, hopefully, we will increase our validation accuracy as well as the training accuracy. So with that, let us get into today's lecture. So in this lecture, we will discuss a few ideas. First, we will talk about how deep neural networks that includes convolution operation can learn some specific features in those images. And we will also discuss how the problem of overfitting arises in these models and how you can detect that. And then after that, we will spend the majority of the time in today's lecture in 4 techniques: regularization, which improves the model's ability to generalize the patterns in the training data so that during validation, it performs better. We will learn about dropout, which is also another regularization technique, but here it's slightly different from how regularization is normally implemented. We will discuss the details of this, so don't worry if you are not familiar with these terms. We will discuss about early stopping, where we don't run as many number of epochs the moment we see that the validation accuracy is starting to decline. So we will decide to stop training the model early before the validation accuracy starts declining, because when it starts to decline and when the training accuracy starts to increase, it's a classic sign of overfitting. So once that starts to happen, we don't want to train the model anymore. And we'll also discuss at the end of the lecture a very powerful technique called batch normalization, which is used for normalizing the values that are going into a layer of the neural network so that the mean is close to 0 and variance is close to 1. So all these 4 techniques we will individually explore. And at the very end of the lecture, we will also implement in code on our 5 flowers dataset a model with all these 4 techniques applied at the same time to see how much of a good model we can get as a result. So this is the agenda of today's lecture. So why are we keeping on exploring deep neural networks? Because as you might have guessed, the direction in which we want to go in this course is towards convolutional neural networks, because you know that they are the most efficient types of neural networks for image processing. And we want to go in the direction of transfer learning. And all of these are deep neural networks, right? So why do we go deeper? Meaning, why do we add more and more hidden layers? Because unlike any other universal function approximators, which can approximate pretty much any pattern you see in a function, because at the end of the day, the data that is presented in the form of images are numbers in the pixels, right? And this can be hypothetically represented using some sort of function. So we are trying to build a universal function approximator. Fourier series is one example of universal function approximator. But if you look at deep neural networks, they are much more efficient in terms of number of parameters to be used for approximating a certain function. So that's the reason why they are called parameter efficient. The second thing is these deep neural networks can actually, unlike shallow networks we explored in the lecture 3 and 4, it can detect not just edges in the images, it can detect textures within the edges, which will help us detect objects. So these 2 images at the bottom here, it shows just as a demonstration, the idea of detecting edges and textures. So in shallow neural network, it may be good at detecting overall shapes. So if 2 circles versus 2 squares are there, if they are approximately squares and approximately circles, these shallow neural networks may still be able to detect circles from squares. But if there was an additional layer of complexity, which we had to detect to make classification that the circle 1 and square 1 belong to category A and circle 2 and square 2 belong to category B because of maybe some sub-textures within these edges, to detect those. So in this image, there are edges, broader edges, but there are also textures on the edges, and such finer level of detail for capturing those, we need deeper neural networks, because these deeper neural networks have more number of parameters and more number of layers, which can learn more complex patterns in the input data. In this case, this input data is in the form of images. So this is why we are using deep neural networks, because even for big resolution images, we can have deep neural networks. So it's a very scalable approach. Now, overfitting happens, as I mentioned earlier, when we have training loss that is continuously decreasing, meaning the model is becoming better and better and better at understanding the patterns in the training data, but model is becoming worse and worse and worse on the validation data. So the validation loss, denoted by these dotted lines, it's increasing, whereas training loss is decreasing. And this is not at all good, because this is as if a student is learning for an exam by hearting the textbook. The student may know every single thing that is there in the textbook just because he or she learned it by heart. But if a new concept comes which is related to what is taught in the textbook, he or she cannot answer. He or she doesn't know how to think about it because the student is too focused on rote memorizing the data. So that is exactly what happens in overfitting. And this is bad, because this is not why we are building the neural network in the first place. We don't want a neural network to rote memorize data. We want it to perform by learning the general patterns in the data so that it can make predictions on unseen data set. So as I mentioned, these are the two symptoms. Training loss is initially initially high, and then it becomes low. Validation loss starts to increase. So here, please note, we are talking about the loss. If we were talking about accuracy, it will be exactly opposite. Validation accuracy will be less, training accuracy will be high. Now, we want generalization. We don't want the model to learn specific noises in the data. We want the model to learn general patterns in the data. And what this means is, if you have an overfit model, it will almost always make on real life data incorrect predictions. So take a look at this example. So here the actual observed data are these crosses, these X. This is the actual data. Okay. Now imagine we are training a few different types of models. A model that is overfitting, underfitting, a model that is fitting the data points really well, and a true function using which this data, meaning the true physics of the problem using which this data was experimentally generated, because in experiments there is almost always noise. So maybe the problem that was being observed here was maybe the propagation of a wave. So here the true function, denoted by these black dotted lines, it's like a sinusoidal wave. But this sinusoidal wave is only happening in theory. It can be described by y equal to sine of x. Okay. But when you make experimental observations of the height y as a function of x, x can be position, x can be time, whatever it is, you may get experimental observations like these crosses. So they are a bit noisy, but they are in general following this true function. All right. Now, what will happen if a function is excessively memorizing this data? Then instead of the function learning the general idea that this data is like a sinusoid, it will start learning patterns based on the noises appearing in the experimental data. So look at this this overfit function, which are these red dotted lines. So this red dotted line perfectly passes through most of the experimental data points. You can see that when there are outliers, this is not exactly outlier, but when there are data points which are far away from the actual phenomenon, the model will try to fit through that. And this is when you have an overfit model. And this is not good, because if you track these red dotted lines, you see that they are not at all following a sinusoid. Ideally, in this case, if overfitting was not there, what the model should learn is that this data, the The general pattern that the model should learn here is a sinusoidal pattern. A totally underfit model will not follow any pattern in the data. And so here this straight line, dotted straight line, yellow line, it's an example of underfit data. This red dotted line, which I discussed earlier, is an example of overfit line, overfit model. A good fit is something that looks like this orange line, orange solid line. It is not exactly following the sinusoidal wave, but it is also not exactly following the experimental data. It is somewhere in between. So this solid orange line is respecting two things. It's respecting the physics of this particular experiment that generated the observed data, but it's also kind of respecting the experimentally observed data because it's not too far from experimental data. So it's kind of the best of both worlds. And that is a good function. It's a good fit because it can generalize. And now if somebody is asking, hey, what is the value of x, value of y when x is this, x is let's say 1.2, then hopefully it can predict accurately that the value of y would be somewhere here because the model is following this trend. On the other hand, let's say if somebody is asking what is the value of y when x is minus 0.2, then this overfit model may predict something like, oh, when x is equal to minus 1.2, y is somewhere very low. But maybe in reality, the y has to be somewhere here. So it depends on how exactly the model is. But the point being, a good fit model is the best thing that you want to have. Overfit is not good. Underfit is also not good. And underfit is anyway not a problem that we are dealing with because the models that we are building is supposed to have at least good training accuracy. So the problem that we were facing was there was some training accuracy, but validation accuracy was diminishing. All right. So let us discuss about not 3, but 4 ways of preventing overfitting. So let me change this to 4 because we are, along with these 3 methods I discussed, we are also going to discuss batch normalization. So we'll be discussing about regularization, dropout, early stopping, and batch normalization. And hopefully one of these techniques or a combination of these techniques will help us have a better model that learns the general patterns in the data, and the validation accuracy will hopefully become better. All right. So we will start with regularization. Regularization is very famous. I'm pretty sure you have heard of this. If you haven't heard of this, no worries. I will explain it to you as if you are a complete beginner. But regularization adds a penalty to the loss term. So this is what a neural network does, right? A neural network tries to make predictions on the data. If the prediction is far away from the reality, then it means the loss is high. Loss can be of various types. In regression, an example of loss is mean squared error. In classification, an example of loss is cross entropy loss. So here, what we do is, irrespective of what model we have, whether it is classification or regression, we add a penalty term to the current loss. So if the loss is mean squared error, like the vanilla mean squared error, or just the mean cross entropy loss, we will add a term like lambda times sigma modulus of w square. Not modulus of w, actually just w square. Modulus is actually not needed. So here w is each of the weights of the model. So if the model has 10 weights, this is like a summation of the square of weights. Here also it's a summation of weights with index I. So there are 2 types of regularization, L1 and L2. So this is L2. L2 is called as ridge regularization, and this is L1, and L1 is called as lasso regularization. In L1, the penalty term is like this, lambda times sigma mod w, and in L2, it is lambda times sigma w square. So think about what's happening here. So if the model, for whatever reason, if the model weights become very big, then the model is getting penalized, because if the weights are big, this loss term lambda w square or lambda mod w, that loss term, that extra term will become big. So that means the model won't be able to minimize the loss. So basically what we are doing here is penalizing the model for constructing weights that are too big. And why do you think constructing weights that are too big adds to overfitting? Because we claim that this is being done for preventing overfitting. So how does preventing the model from having big weights prevent overfitting? That is the biggest conceptual question that you can think of in the context of regularization. So Just have a look at this. If a model has to overfit through these data points, it has to have more number of weights with big coefficients. So if we wanted the model to perfectly fit, meaning overfit through these data points, we might need a higher order polynomial if we are looking at polynomial regression, which means if we add the sum of the weights for each of the terms in the polynomial, it will turn out to be a big number. Whereas if we don't care about overfitting, if we just want to find the general trend, even like a second order polynomial might fit through the data. So which means you don't have as many number of weights, and if you add the summation of those weights, it won't be a big number. Another conceptual way to think about why big weights are a problem is that if weights are big, what that means is slight changes in input will cause big changes in output, which is usually not a good thing, right? Because when does slight change in input cause big change in output? Let's draw an example. So let's say I have some data set like this. So this is feature 1, x1, and feature 2, x2. And I'm having some data points like this. Okay. So these are all belonging to class 1. And let me copy paste this data to create a boundary. And I'll also change the color of this to green so that we have two classes of different colors. All right. Okay, so now you have two classes, and class 1 is red and class 2 is green. So this is not class 1. This is class 2. Green is class 2. Let me just delete this. Okay, so now let us think about a good model that can make separation between these two classes. Maybe a good fitting model might be something that goes like this. And here, whatever is above the straight line may be belonging to this class 2. Whatever is below the line may belong to class 1. Okay, now let us look at an overfit model. All right, an overfit model may look something like this. It may go through its decision boundary may be going like this. Oops, sorry, this should be part of. So this may be the decision boundary of an overfit model. Now, can you tell me the problem with this model? The problem with this model is that, so see these 2 points are very close to the decision boundary. Okay. So if the weights are big, meaning if the points are close to the decision boundary, because that's when weights are big means slight changes in input causes big change in output. So let's say the input, meaning this x1 value of this green point is slightly changing. Like it's slightly changing here. Then what happened? X1 only changed by very little, but now it is inside the other, it's on the other side of the decision boundary. So the class of this changes to red. And this is a problem, right? Because in real life, small change in input should not lead to such drastic changes in output. And that is a classic sign of having an overfit model. And this happens when weights are big. So, or if there are more number of weights to even make this fit happen in the first place. So if you take a summation of absolute value of weights, or if you take a summation of square of those weights, it will be a big number if a model is a complex nonlinear line like this. If it's a simple linear, I mean, of course, there are nonlinear cases where we might need a not straight line to fit through the data, but not something overfit or complex like this, right? Often we want to find the general pattern or the general decision boundary that generally separates between class 1 and class 2. So if the input is slightly changing, it should not cause a drastic change in the output prediction. And that happens only if the values of the weights are not so high. And that is what regularization exactly does. It prevents by adding an extra penalty term in the loss, either through L1 or to L2, where lambda sigma W square, if weights are big, this term is big, which means loss is high. So model is incentivized to bring down the weights in L2. In L1 also same thing happens. There are more differences between what L1 exactly accomplishes and what L2 exactly accomplishes. I have made a very detailed lecture video on this topic already. I can share the link with you, so please have a look at that. That covers the finer differences between L1 and L2 regularization really well. But for the purposes of this lecture, for making our deep neural network better, we won't be going into the details of how exactly does L1 perform better in some cases compared to L2 or vice versa. Let's not discuss that. Now, here, what we want to know is, can L1 regularization make our validation accuracy better? Can it reduce overfitting? Because here the training accuracy is keeping on increasing, whereas the validation accuracy is decreasing. Can this regularization do that? So let's see how to implement regularization in our model. So our code does not change even slightly to implement regularization. Implementation is very, very easy. So without regularization, this was how our model was in the previous lecture. So we had a TensorFlow Keras, and we were defining the layers sequentially. So first we had a flatten operation. So flatten meaning the input RGB image was flattened. So image height and image width was the input. Image channels was 3. So this height was by default 224, width was 224, channels RGB 3. Then we had a dense fully connected layer from flatten to the next layer. And in this, what we did was we defined a configuration which kind of held the number of hidden nodes. This was done because in weights and biases, we wanted to do hyperparameter tuning. So we tried 128 nodes. We tried 64 nodes in the hidden layer. In today's lecture, we'll be using 128 nodes. So this value of this config.hidden nodes will be 128. And we were using activation function as ReLU. Then the last layer was one with softmax activation. And here len of class names is 5 because there are 5 classes. So last layer has 5 nodes and the activation present is softmax. So this was without regularization. Now with regularization, all we need to do is we define the regularizer as tensorflow.keras.regularizer. So L1, L2, the coefficient of L1 is 0, meaning L1 we are not applying. For L2, we have 0.001 as the coefficient lambda. And the only place where we make a change is in this, in the hidden layer, where we say kernel regularizer equal to the regularizer that we defined over here. And this tells the model that implement regularization such that the value of lambda corresponding to L2 regularization is 0.001. That's it. Just one small change. In the output layer also, we apply the kernel regularization with regularizer. And this tells the model that the weights in the between hidden layer and in the final layer before applying the softmax, apply regularization. So hopefully this will prevent the weights in those layers from being extremely big, and hopefully this will make our model better. So I have already run the code by making this change. So let me first show you the code. So in our code to implement regularization, it's fairly straightforward. So last time we had a few different parameters. We had batch sizes of 8 and 16. So I deleted 16 because from our hyperparameter tuning, I realized that the best batch size is 8. Best is 0.0001 for the learning rate, 128 hidden nodes in the hidden layer. And image size, instead of 224 by 224, 16 by 16 was working better. Maybe once we have more complex models and when we are implementing transfer learning, we will come back to a bigger image size, because I am fully aware that we are having a lot of loss of information here. And epochs, instead of 5, we are using 10. So these are the changes in the hyperparameters, which are the results of our hyperparameter tuning from earlier. And in the code, implementing regularization is fairly straightforward. So let me just open the Google Colab notebook where we implement that. So in this notebook, which I just opened, let me make sure that the hyperparameters are the correct values. Previously, we were using, as I mentioned, 8, 16, like we were doing a sweep of various hyperparameters. This time we are only using the optimal ones, and this is not needed. And then in the part where we define the model, all we need to do is, let's go back to our code. We just need to define the regularizer and then add that in the hidden layer as well as in the final layer just before activation. So let's copy this code and let us paste it here. So model equal to sequential keras.sequential, and regularizer we are defining as L2 with 0.001 as lambda. We can also try with 0.1. So there are various things which you can do. I think initially it's better to start with 0.1 because you are penalizing the big weights a bit more. 0.001 is too small. So then anyway, you will have to do a hyperparameter sweep. And yes, that's pretty much it. You can run this code. I will just show you running the code, but results I'm going to show you anyway directly because executing the code is going to take some time. But let me first show you that the code can be fairly easily executed. And here, what is going to happen is when we run this part of the code, it's going to ask an API key. So as I showed you in the last lecture, if you are using weights and biases, you will of course need the API key from your weights and biases account. If you don't want to use weights and biases, it's again fine because if you don't want to log your experimental results here, you can just directly run it on Colab and take your results from Colab itself. So here, when it asks the key, I just copied it from weights and biases and just pasted it here. And then I run this part. So everything is looking fine. And then I call this weights and bias agent. And now the execution has started. So this will keep executing for, I think, several minutes. For me, it was taking definitely 30 minutes or more, if not less. So 30 minutes minimum, if not more. So let's go to the results to see what we have. So after we implemented regularization, we were getting something like this. So this red curve is the training accuracy and this blue curve is the validation accuracy. And you can see that unlike the previous plot that we had, let me copy this plot and paste it here for side-by-side comparison. So here you can see that training accuracy was again keeping on increasing before we implemented any regularization. It was going above 0.525 after 5 epochs. Here we have run already 10 epochs and you can see that validation accuracy is not coming down, meaning overfitting is not happening yet. But here in this graph from our previous experiment from last lecture, there is definitely overfitting happening. And more importantly, look at the values of these accuracies. So here after 10 epochs, training accuracy is close to or above 0.6. So I think it's close to 0.61 or 0.62 or something like that. Validation accuracy is above 0.5. Here validation accuracy, the peak of validation accuracy was just 0.375 and it had already started overfitting, which is why validation accuracy had started to dip. And training accuracy was still continuously going up above 0.525. So clearly adding regularization has helped us to make the model better because overfitting has been, at least till now, we are not seeing overfitting. So this is definitely good. But obviously, one thing you might be disappointed at is maybe you were expecting the results to jump from 0.5 to 0.95 or 0.99. Of course, that's not going to happen. And we will do that. We will see how to have deep neural networks with very high accuracy, because in traditional, if you have worked on problem statements from Kaggle by implementing convolutional neural networks on some image data set, accuracies that are typical for 2 class, 5 class classification is like 0.9, 0.95, 0.99, etc. Here, even with regularization, you are still at 0.6, 0.5, right? So there is definitely not a tremendous improvement, but there is some improvement. The main takeaway from here is not about the improvement in accuracy, but it's in the fact that we have been able to reduce or minimize overfitting. And this is definitely going to help us once we implement transfer learning and once we implement convolutional neural network in the later lectures. So just understand that by penalizing the models from choosing big weights, we now have a model that learns the general patterns from the training data. And because of that, it's performing decently on training data. It's also performing kind of well on validation data. All right. Now let's look at the next technique which we can use to prevent overfitting or minimize overfitting, and this is dropout. Dropout is also a very famous technique. It's in fact another regularization technique where we randomly switch off certain nodes in the layers of the neural network. And when I say switch off, it simply means, just look at this image. In this image, half of the nodes in this hidden layer has been switched off, meaning it's not part of that particular training cycle. So although there is a connection that is drawn from this node to this node, it's as if it does not exist. So this node is completely not part of the training. And here it's like a dropout with a parameter 0.5, meaning 50% of the nodes are selected at random and they are now not part of the training process in that training set. And here you can see that these two nodes are not part of the first and third node. Here the middle two nodes are not part of. And this is an example of dropout with dropout parameter being 0.5. So the formal definition of dropout is that with a probability p, where p equal to 0.5 or 0.2 or whatever, a particular neuron is set to is drop, meaning it is set to 0. So whatever output is coming from that neuron is set to 0. There is nothing. It's as if there is nothing is coming out of that neuron, right? And with probability of 1 minus p, it is kept as normal. So whatever weights are there in the neural connection between that neuron and the prior neuron, all of that will be like that. So this will kind of make sure that if p equal to 0.5 that we are using in dropout, half of the neurons will be used and half are not used. If p is 0.3, 30% of the neurons will be sort of turned off, remaining will be used. So this is how it is used in training. But now you may have a doubt, okay, this is how it is done in training and during inference. So what we do? During inference, we are not going to be using dropout, but the outputs from these neurons are scaled accordingly. So what does that mean? So let's say in the training, the net output from here was due to just 2 neurons, right? But in reality, output from 4 neurons were expected. So half of them are missing. So whatever output is coming out of the activated 2 neurons, they will be scaled by a factor of 2. So that is what I mean by scaling the outputs in the neurons. So what is happening here is for each batch in the data set, so data set is divided into a bunch of batches, each batch will see a slightly different neural network. Why? Because you can't predict which exact neuron is going to be switched off and switched on. So you can safely assume that if it's a big neural network, deep neural network where dropout is applied across multiple layers, it's almost sure that each batch of training, meaning if it's a batch size of 8, there are 8 images that are part of that training batch. Those 8 images will see a different neural network than the prior 8 images or the next 8 images. And then this is what scaling means. In scaling, if p equal to 50%, meaning 0.5, then you are scaling up the output from that layer by a factor of 2. If p equal to 0.25, then you may scale by a factor of 4, because now instead of if p is equal to 0.75, it means you are switching off 75% of the neurons. Only 25% of the neurons are available to provide output in that layer. So the output is scaled by a factor of 4 in that case to make up for the lost activation. So this is how dropout is implemented. And just think about it for a second. Why dropout is helpful? Why does switching off some nodes or some neurons in these layers help? Because then you will prevent any of these neurons from over learning from the patterns in the entire training data, because this neuron may have gotten exposure to some part of the training data, but not to the entire data. Similarly, this neuron might have seen another subset of training data during the training process, but not all of the data, because this was probably switched off at a probability of p. So if there were 100 set of training runs that happened, in that if p is 30% of the times this neuron was off. Remaining 70% of the times only it was on. And during those 70% of the times, this was seeing a set of image batches, which were probably different from the set of image batches that this neuron saw during its on time. So this, to a great extent, will prevent the neurons from over learning the patterns in the entire training data set. So implementing the dropout is also extremely simple. So these were our layers, right? So we had flattened layer, then we had a 128 node hidden layer, and then we had a final layer with 5 classes and softmax activation. All right. So this was our model. When we have dropout, all we need to do is if we are dropping out in this layer, we can add a corresponding dropout right after that with a probability of 0.5, which means it will mask 50% of the neurons at a randomly from this layer. So that is what's going to happen. And let's see what is the effect of this dropout. And implementing this dropout is also fairly straightforward. So if we go back to our code, and you can see that the code that we previously started to run for regularization, it's still running, but only 30% of it is finished. So it's again going to take maybe 20 minutes to execute. It's already been running for 9-10 minutes. So let me stop running for now. And what I'm going to do here is let me remove this regularization, because we just want to try dropout without regularization. And if I want to implement dropout, all I need to do is copy this part, keras.layers.dropout, and paste it here. So this will implement dropout, and this is anyway not being used. So I can just comment this line, regularizer is not being used. Everything else remains the same. So it's fairly easy. And if you want both, you can add both. If you want both regularization and dropout, keep this line. Let me remove all these things. So now regularization is there in both of these layers. And on top of that, I want dropout also here. So now in this setting, both regularization, L2 regularization and dropout is being applied. I mean, dropout itself is a regularization, but instead of, it's a type of regularization, but it's not an L1 or L2 regularization. So here we are implementing both, but let's not do both. Let's only do one thing at a time. So I'm going to delete the regularization part in the code. And yeah, so now this is our model, and we can run this model also. So let me show you the result from this model. Just one line change right in the code, but still the output is surprisingly good. So here are the results. After dropping out 50% of the neurons, we have 10 epochs here, and this red curve is actually the training accuracy, and the blue dotted curve is the validation accuracy. You can see that after some, so it's surprising to me also that initially validation accuracy is higher than the training accuracy. That's definitely surprising to me. But eventually you can see that both of these accuracies are going on increasing. They are very close to each other, and there is no sign of overfitting yet. It's not like training accuracy is much greater than validation accuracy, and it's not like validation accuracy has started to dip. I don't see any signs of that. So here definitely we can see that until these many epochs, we have run for 10 epochs until now, there is no overfitting happening. Unlike this case, unlike here, let me again copy paste our previous graph. So this was our original graph in the absence of any kind of overfitting prevention. So if you compare these two graphs, you can clearly see that accuracy has improved. So here it has reached 0.5 accuracy. What has reached 0.5? The validation accuracy as well as training accuracy. You can also look at epoch 5, because here we had run 5 epochs. So here at epoch 5, the training accuracy and validation accuracy are close to 0.45. Whereas here it is, here validation accuracy was close to 0.35. Training accuracy was close to 0.52. So clearly you can see that both are kind of, training accuracy has slightly reduced, but validation has significantly improved. And that is exactly what we want for a good model. So these are the results from the dropout. And as I mentioned earlier, even for implementing dropout, it's going to take some time to run the code. It will take you at least 20 minutes. So 20-30 minutes depending on your configuration. But I will share the code with you so that you can run everything directly. All right. So now with that, let us get into the third overfitting prevention technique, which is early stopping. Out of the 4 overfitting prevention concepts that we discussed today, early stopping is definitely the easiest one, because early stopping, as the name suggests, stops the training before the validation accuracy degrades too much. So an example of where a good place for preventing overfitting in this example could be that you can figure out when the validation accuracy is starting to decrease, and then you can decide like a cutoff. So you look at the validation accuracy, and if it has been decreasing continuously for 3 epochs, for the past 3 epochs, then you can decide to stop. So here in this example, it's impossible to stop at this point, because after the 4th epoch, you have the highest accuracy, and then it has only decreased for 1 step. So you have to run for 6th epoch and 7th epoch, and then maybe you can decide to stop training, right? But you can define the patience. So there is a parameter called patience. Um, so this is the code, right? So what you do is you say you monitor. So you have tensorflow.keras.callbacks. So here you define the early stopping. You call the early stopping function where you monitor validation loss. And here you define patience equal to 3, meaning for continuously 3 epochs, the accuracy is decreasing, the validation accuracy is decreasing, you stop training at that point. So the graph that you see here below is the perfect example of early stopping demonstration. This was done earlier. However, if patience was 1, then what this says is even if for 1 epoch, if the validation accuracy decrease, you stop training. But that is not good because validation accuracy, there will be some undulation, right? It's not expected to always increase epoch after epoch. But let's say if patience equal to 2, it means you look for consecutive 2 epochs. If for the last epoch and the epoch before that, the accuracy has been decreasing, then you stop immediately the training process. So that is what the early stopping is. I'm not running this code to demonstrate it, and because I have run the code only for 10 epochs and I haven't seen continuously degrading validation accuracy in many of my experiments for continuously even for 2 epochs. So because of that, so far I have not been able to experience early stopping, but this is a good thing to keep in your code, because in case if in any of your training runs, if you are experiencing degrading validation accuracy, then you can automatically stop. So it's just one line of code, right? You are just implementing this callback in the model.fit. This WNB matrix logger is anyway different. That is for logging your training outputs into the weights and biases. So this is not the line that you should pay attention to. Just pay attention to this part in the callback. So if you add this callback, it will automatically take care of stopping the code early. So early stopping is fairly easy, right? Now let's come to the last part of preventing overfitting, batch normalization. Batch normalization is again a cool concept. It's fairly something that is straightforward. It is if your inputs are like this. So let's say your original data set belongs to some part of the space. So if you have n-dimensional data, it's like an n-dimensional hyperspace. So if in that hyperspace, if your data belongs somewhere, you normalize the data such that the mean value is 0 and variance is 1. So you do that, and that process is called as batch normalization. And you do this over batches. So you have a batch of 8 images, and each image, let's say it's a 32 by 32 pixel. Then you have that many dimensions in each image, and then you have data points, right? You have images. Each image, let's say it's a batch of 8 images. Then you have 8 data points for each image, and each image is having 32 dimensions. And then what you can do is you can normalize the pixel values such that you bring the mean to 0 and variance to 1. So this is also another example of the same thing. You have a data which has huge variation along x-axis. Along y-axis, the variation is a little bit. Mean is not 0, but here you brought the mean close to 0, and the variation along each of these axes is now converted to unity. So this is called as batch normalization. And this is also indirectly, it will help us regularize, because the variations happening in the data set from one batch to another, meaning statistical variation, because each batches will have different variance and different standard deviation. If you are talking about pixel values, depending on which 8 images you are picking, the average value of the pixel intensity and the standard deviation of the pixel intensity values will be different. It depends on the batch sizes. So when you are normalizing one batch and another batch separately, it means you are automatically reducing the tendency for the model to overfit, because you are taking batch characteristics also into account into the data while normalizing, not the entire training data set. So indirectly, it helps you perform a little bit of regularization, and this will also prevent overfitting. In fact, as I'm going to demonstrate to you, what worked for us, for me, the best is batch normalization. So before I show you the code is again simple. Let me first show you the output. Okay. So this is what I obtained after batch normalization. This red curve is the training accuracy. This blue dotted curve is the validation accuracy. And you can see that after 9 epochs, it even reached close to 0.5. Before, when we implemented regularization, I think here we got around 0.5, right? This was just dropout. Here also we got around 0.5 as the validation accuracy, but training accuracy was also 0.5. So that was another issue. In just the regularization, here we got 0.6, above 0.6 as the training accuracy, and slightly above 0.5 as the validation accuracy. So this was with L2 regularization. But now with batch normalization, look at the training accuracy. Training accuracy after 10 epochs is now, I think, close to 0.8, almost close to 0.8. And this is the highest training accuracy I have ever received without convolution and without transfer learning on this 5 flowers data set. And this is amazing, right? The validation accuracy, it has started to decline a little bit at the 10th epoch, but it's still fine. It's not like there is a tremendous decline. And maybe we have to train this a little bit more for improving the validation accuracy. But this is in general a good sign. Of course, there is a little bit of sign of overfitting here, meaning validation accuracy is not tremendously improving, although training accuracy is improving. But even to get this kind of a training accuracy with just 10 epochs, it was very, very difficult for us with our earlier model, like with the current model without batch normalization. Now let's see how to implement batch normalization. It's again done in this keras.sequential part. So here, look at where we are implementing batch normalization. We are implementing it here after the this config.hidden node. So we do this just before sending the values into activation function. Then here also we perform batch normalization of the inputs that are going into the softmax activation function. So these functions are already defined in Keras. So we just need to call it, and we just need to make it part of the Keras layers. So this is the first layer, right? This is the flattened layer. This is the layer where you have 128 hidden nodes and ReLU activation. And just before you pass the value into ReLU activation, you are performing batch normalization. And this is the last layer, which has 5 nodes because there are 5 classes, and you are performing batch normalization, and then you are implementing softmax activation to get the final probability distribution of the classes. And once again, let us compare the outputs that we had in the absence of any of this versus with batch normalization. So this figure was this plot of training and validation accuracy is what we had before we implemented anything to prevent overfitting. And here you see 0.52 was the training accuracy, and the validation was decreasing already after 4 epochs. Here you can see that you have a steady validation accuracy more or less, and it has reached close to 0.5. Maybe in the subsequent lectures from now, we can start running for more number of epochs, maybe 40 epochs, 50 epochs. We have to see whether how much the validation accuracy is going to increase. But I'm so happy to see this tremendous improvement in training accuracy. Now, what we can do at the very end is let's apply all 4 at the same time. So we apply regularization, dropout, early stopping, and batch normalization. So before implementing any of this is how our code looks like, right? This is also not there. So our code looks something like this. In the model, we have sequentially 3 layers: flattened, the middle 128 node hidden layer, and the last layer with 5 nodes. Then we call the model.fit function. This is before part, meaning before implementing any sort of overfitting prevention method. And after doing that, this is what we have. So we define the regularizer, and we call the regularizer with L2. So what we did here was, let me put back the code. So what we can do is define the regularizer tf.keras.regularizers L1, L2. So here it is L2 with 0.1, let's say, as the parameter, lambda parameter. It defines the strength of regularization basically. And we are using the regularizer in the first dense layer and also in the last layer with 5 nodes. Then we are performing batch normalization in the first dense layer and in the last layer also. And last thing, we are performing early stopping. So early stopping is defined in this callback part, where the patience is defined to be 3. And also we are implementing dropout with p equal to 0.5. So with this code, we are implementing all the 4 things. And let's see what the output looks like. So after implementing everything, regularization plus dropout plus batch normalization plus early stopping, our accuracy looks like this. So the red curve is the training accuracy and green is the validation accuracy. Validation accuracy after 9 epochs, it has touched close to 0.5. So this drop is not necessarily a sign of overfitting yet, because here also the such drops have happened and then it has again started to improve, and training accuracy is still continuously improving. So we have prevented overfitting as much as possible. And of course, we have to compare it with our previous case, right? With this case, where validation accuracy was clearly starting to decrease and it was anyway low in the first place. So compared to this, we have now a much better model. And hopefully in the next following lectures, when we are implementing our convolutional neural network model with transfer learning, meaning pre-trained neural network, when we use, we will definitely be implementing, and if we are training it on a new data set, we will be definitely implementing dropout, regularization, batch normalization, and early stopping. And this is a good practice. If you are building a neural network from scratch by defining it layer by layer, you must do this, especially if your accuracy is not good. Now, when you compare this with the linear model accuracy was 0.35, 0.4, etc. A random classifier will be 0.2 because it's a 5-class classification. Now, with this model with no convolution, you still have 0.5, close to 0.5 as the validation accuracy. I would call this as pretty good. Now, I'm sure even at the end of this lecture, maybe you were expecting more. Maybe you thought after preventing overfitting, you thought we may get a significant jump in classification accuracy. No, that is not the case. We have prevented overfitting, but the improvement in classification accuracy is not like from 0.5 to 0.9, but we managed to bring the training accuracy significantly higher. After batch normalization, we got it to 0.8. We got the validation accuracy close to 0.5, especially after dropout. So definitely there is improvement, but we have to implement few more things like transfer learning and convolution operation to get even further accuracy. And we will be doing those in the next lectures. So with that, I think it's a good time to wind up today's lecture, and let me take a moment to appreciate you for reaching this part of the course. It's definitely not easy to, these are a bit dense topics. You have to code yourself, because a lot of these things are implementation along with theory. So you have to code yourself while watching the lectures. So I really congratulate you for reaching this part of the course. I'm also so glad that the last 7 lectures you have been continuously following, and I'm also hoping to see you in the subsequent 20 or so lectures, 25 lectures also. In the remaining lectures, I will hope to see you. And with that, thank you so much. We will meet again in the next lecture. Take care until then, and bye.